Okay, thank you very much to Walter for organizing these sessions and to Ignacio for inviting me to come. It's always a pleasure to come to this school where I became an engineer. And actually, when Ignacio called me to talk about microwave photonics, I had to think, well, let's see what I can talk about. And of course, then I thought, okay, let's talk about what I'm doing now, which is, I think it's really interesting. So, but I had to give it a sort of a nice flavor. So I'm going to talk about waves on chips. I work on integrated microwave photonics. And I want to let you know how difficult it is to get the waves out of the chips. That's a problem we are working on. And actually, first of all, I'm Guillermo Carpintero. I'm in Carlos III University. I wanted to introduce a bit myself, so you know a bit more of what I do. And most interesting thing we are doing right now is that based on what I'm going to talk to you about, we launched a spin-off company with funding from Bullnet investment. It's a new jump. And as you can see, I'll talk about this in a part of my talk about the leap. That's a new leap I've taken. And basically, first thing, when I saw the workshop, microwave photonics, so I thought, okay, I have to do one thing. First thing I have to do is this disclaimer. I'm not going to talk about microwaves. I'm going to talk about more than microwaves. We are working on millimeter waves and terahertz, which is the frequency final frontier, because it's where it meets photonics. So in my talk, microwave photonics, I'm actually going to talk about how we meet these two ranges, which basically are no more than waves. They are brothers. And that's first thing I wanted to say. Actually, they are brothers, but maybe you can actually say it's like man and wife, man and woman. There was this book that was titled "That Men Are from Venus" and "Men Are from Mars," or the other way around. I don't know now. There are so many planets for the genders that are today, but means that they are different. On one side, we put radio frequency, where microwaves live at this end. And this is where we use electrons to do the job. You process our signals, take them, actually put the signals in a format that we can work with them. That's all about the electronics. We want just our signals, temperature, messages, coding, images. We want to put them in a format we can work with them. And that's the electronics side, using electrons. On the other hand, we have the other end, where the photons do the job. And that's where we can, well, that's why we see. We have photons that are actually shining all the objects so we can see. And actually today, probably we have cut the gas and we are using electrical heaters and we get infrared radiation out of them to heat us. And this is where photonics are in that domain. So in that sense, we have always been working with one or the other. And actually, you can, this is from Elliot Brown, the father of photoconductor, that actually, you can actually think on this on the microwaves and actually radio frequency. As I said before, this is more than microwaves, it's all the frequencies, is all the electronics waves. You can think of being the classical region, and that's where the photon energy, because yes, radio waves have photons associated to them. And the energy of the photons is very small. And basically, that's we work with voltages and currents. And because the energy is low, the wavelength is huge. And this is the key factors or the key issues that we deal with when we're using electronics. And that's why, no matter what, the resolution of radio frequency cameras is low. It's because the wavelength is large. It's nice because when you build these connections in the circuits, the wavelength is large. So basically, you assume that you have a 1 voltage over the entire line. Actually, well, to compare with, PCBs are in the tens of millimeters range, and the wavelength, even at 2.4, is 12 centimeters. And this is actually a source that you can buy in internet for a few euros. And we actually have DC connectors or to bias, and this is the RF interface with a standard coaxial connector. On the other end, that's the quantum region. That's where photons are, because it's quantums of energy. And this is where it's the opposite. That's why I said one's come from Venus, the other are from Mars. It's because it's just the opposite situation where you have photon energy is extremely high, and you have that the wavelength is extremely small compared with the size of the features of your circuits. And this is where the microwave photonics are, the photonic circuits are, where you have micron scale waveguides where photons travel through and do the job. And we can put our information, we can put our signals in the photons and process them as Jose has just mentioned. So it seems that these are two extremes. And yeah, like between Mars and Venus, we have the Earth. Between microwaves and photons, there is a Terahertz gap. There is a gap. And there is a gap basically because in the region in between, it's what it's called the transition region. It's when, okay, we're working with photons, are we working with particles? It's in between. So it's hard because basically you are still working with electrons, but they are behaving with waves. And actually, they are indistinguishable because photons are also waves. We are used to that. That actually, the theory of light as waves is much older than photons, particles. That was actually Albert Einstein's Nobel Prize. He got the Nobel Prize not for the relative theory, he got the Nobel Prize because he explained the photoelectric effect, saying, okay, look, light is a particle. And on the other end, Louis de Broglie actually got his Nobel Prize saying, look, you know, electrons are a wave. And this is the region where you don't know if you have a particle or a wave. Actually, you are working with a particle, but it's a wave. The electrons at these frequency ranges are waves. And that's what makes it so difficult. Because actually, then your tracks are no longer a metal line that connects 2 points with a voltage. You actually have a wave that it's propagating through that line, even if it's a metal and you are putting a voltage. That's what makes it so difficult. Actually, well, there are a few more difficulties. And actually, what I like to see this is that, as I told you, electrons are photons, but these type of photons are huge because the wavelength is big and they have low energy.
So, well, I wouldn't do this with my son. I wouldn't put my son there and put such a ball to him, because even if it's small, it has some energy. But and these are photons. Photons are very small, but are very energetic. And this is what's in between. It's terahertz. Why is there any interest to fill this gap anyway? Actually, there are a few interests. One is communications, because well, this is the frequencies that are being allocated for communications. And as you can see, well, 5G, when it started, they said, we are going to reach into the millimeter wave range. Millimeter wave range starts from 30 gigahertz. And 5G hasn't gone above 30 gigahertz. But now they are coming, okay, in here is a 6G. 6G now they're saying it's going to go into terahertz. I bet that we will not get to terahertz, but probably we will get into the millimeter wave range. And in the millimeter wave range, you already have all these effects. So starting maybe not from 30, but certainly above from 100 gigahertz, you get all these effects. And there are windows above 100 gigahertz. And what is better, there is a lot of spectrum available. That's what we need. But there are other applications that need or are interesting to use terahertz. I like this very much. Is painting, to evaluate the quality of our cultural heritage. One of the great applications of terahertz is that you can measure with high resolution thickness of layers. Basically, paintings are layers one on top of each other. And you don't want to use light, because as I said, light is very energetic. And you don't want to decompose, you don't want to risk the pigments that have been used, especially from unique paintings like the one you see, it's The Last Supper in Milano. It has been evaluated, the quality, because it's painting on a wall. Walls get humidity, and it's not a standard substrate on which to paint. They have evaluated the pigments of this masterpiece with terahertz, because you can see through the different layers. You can measure the thickness, and you can actually measure the effective index. You can measure the qualities of the materials that are in that structure. And that has also commercial use today, and to a more mundane problem, that is what is the thickness of the paint that I'm putting in my cars, because that actually impacts how long it's going to be rust free. So this is done with high frequencies. So there is an interest to fill in this gap. And okay, what are the problems to fill in this gap? I said, okay, it's the transition region where electrons behave as waves, but if that was the only problem, probably would have solved it today. There are some problems. One of them is transmission loss. No matter what transmission media you think of those that are used commonly today, has high losses. And one of the factors that Jose mentioned in these figures of merit was loss. Loss is the most important factor when you look into a system, especially if you need to transmit a signal and detect it. And even microstrip lines, rectangular waveguides, even you can actually see that the atmosphere is even better than any of the other media that you can consider. It's better to radiate than to put it into a microstrip line. Problem is that circuits need microstrip lines. You cannot have free space circuits. It's very difficult to align. Actually, most of the systems that use terahertz were free space, using emitters immediately, and all the processing was done on optical tables with lenses. Problem is that the temperature variations basically misalign the system, so it's not practical. And if you tell an engineer, well, if you tell an engineer might do it, but if you tell an operator to please align the system, cannot do that every day. That was one of the problems actually, because why TeraView produced a system, a terahertz system, to do terahertz imaging, and one of the impracticalities was that they had to align it every day before every use, actually, if it was not in a clean room with control temperature. The atmosphere problem that it has is that as you go up in frequency, and when you reach a terahertz, you see ups and downs. There are different absorption peaks from different molecules present in the atmosphere. And this makes it difficult to use in communications because you have high losses. Actually, some call these steep walls as the terahertz wall. Because actually the terahertz is just in this point. The other problem is related to what I just said, being in the transition region where we don't know what we have. We have both particles and waves. And that is very difficult to have compact sources that generate sufficient energy at high frequency. Because there are some barriers that you can see here. This is basically this is the 20 dB roll-off in electronics. In any electronic system, you always have a resistance, you always have a capacitance, so you are going to have a 20 dB roll-off. And this is this trace. This is 20 dB roll-off, the electronics limitation. And of course, in photonics, well, you generate photons by energy transitions, so you have the frequency the frequency energy decrease of the photons. As I said, electrons have a very low energetic photon. This is the energy curve of photons, and terahertz is just in this crossing point. So it's difficult to generate high energy because if you use transitions between bands to generate your waves, then your photons are very low energetic, so you have low energy. Or if you use electronics and you use electrons moving around at very high speed, you have the 20 dB roll-off of resistant capacitance belts. And as you can see, there are different types of sources that have been devised with different techniques. You can actually, you see that you have solid state, photonics, lasers, electronics is here with MMICs, monolithic integrated circuits. Photonics is here. You see all the green stuff is very low. It's photonics has a problem to generate high frequency signals. Photomixers, photodiodes, and photoconductive antennas. We are down here. And the best the electronics is doing is still 20 dB, 30 dB away from the limit. And only huge installations like gyrotrons can generate enough energy. There are some also vacuum tubes are also being used, but these are bulky. So it's a problem to generate, I mean, they are not compact. So it's a problem to generate compact sources. And I started this telling you, I'm going to talk to you about integrated sources. So we have to use semiconductors. So we are here, and electronics seem to do better. So what can we do? This is one of the first things I'm going to talk to you about, is how we address the problem of the transmission losses or propagation losses. Because those are the problems we have to act on. these two issues that I just showed. Well, one thing, as Jose mentioned, is to use photonics. You convert into the photonic domain. I have my RF signal, I place it in the RF domain, and then I can transmit it. This has an advantage, and this is a paper from '87, so 40 years away. That's when microwave photonics started. And first reason that was claimed to use photonics is that the attenuation of any connector, any transmission media, coarse guided, that we use in electronics has higher losses, namely coaxial or rectangular waveguide. And if you go to rectangular waveguide, you can already see that it's not continuous. You have bands. Photonics is here, and this is a logarithmic scale. So you can actually see the advantage of going into photonics. Oops, so wrong direction. If we put it into figures of merit, this is the attenuation. So cannot do better. In just going to photonics for transmission, you basically get rid of 10 dBs, 40 dBs of loss. The other advantage is the bandwidth. Okay, because okay, I think sorry, because this is the other way around. This is the bandwidth here, and this is optics, and this is the coax. Sorry, because I was too asleep when I did this. Bandwidth product. This is the photonics. So I started with photonics, and then I continued. I swapped even the images. So look at the image, and the only number that we have to swap is this. Bandwidth has a huge. Photonics has a huge bandwidth. So it's not only low loss; it's a huge bandwidth. That's what we get if we go into photonics. And you have as well lower weight. This is interesting for aerospace. And you have smaller bend radiuses, so you can make more compact with fiber. And one of the advantages is that you don't radiate. Because even in coax, you have evanescent wave. So there are many advantages. But not just that, you actually can, as was explained, you can do processing. And actually, this is, first I show you that we could basically transmit an RF signal through the fiber, but you can actually do processing, and you can actually do optical beam forming, so you can get an array. And this is an example of an early demonstrator of beam steering by Satrax company that existed some years ago. And actually they did this demonstrator, and they had this chip to do the optical beam steering. As you can see here, basically we have one input, multiple outputs for our different photodiodes to build the array. This was not good enough, because still the output, these fibers, you know that there is a conference that it's microwave photonics, and there is another conference that is called optical fiber sensors. Problem is that optical fibers are sensors and are the field temperature, and then you can do a true time delay. You can precisely define what is the delay of between these different branches. Then you put them on fiber to take this to the photodiodes, and the phases change, the delay changes. And this is because this system requires fibers to take the signals, optical signals, to the photodiodes. So Satrax was incorporated to Lyonics, and they did a better job. And that's where integrated microwave photonics comes. If you want to maintain the time delay between the different elements of the array. So if you want to maintain the time difference between the RF signals that reach every element in your array, you have to do it on a chip, integrate the chip together. And basically, this is what they did in Lyonics. They actually evolved the previous example that I showed you into an array of photodiodes that it's next to, this is a hybrid integrated device. It's placed butt coupling to the chip that I showed you before with the optical beamforming network. So all of this is in single substrate, and it has same temperature, so you don't have all these differences in time delay that the fibers would induce. Problem is that when they put these photodiodes, still, this is not where the antenna is. They still have to take the signals to the antenna, then they use microstrip lines with time delay to compensate for the different length where you put the connectors. And from here, you have to use a coaxial cable to the antenna. But then we are back in the main problem that we started. Coaxial lines are lossy, and you still have to generate, and photonics doesn't give you enough power to take this to the antenna over a long stretch of a coaxial line. So what do? We do convert this into a photonic signal and send it to the antenna through a fiber. So we are doing photonics on electronics on photonics on electronics on photonics. That's not the solution. And then it's this is when actually we are in the problem of the waves in the chip. This is what I wanted to talk to you about. We need ways to take these signals, because basically what I'm going to put here is a microstrip line. So I'm going to need RF tracks. I need to take these signals down to the modulator. If I have losses, then I'm back in the problem. And we have another problem that it's how do I get the RF signals of the antennas? Because if I was telling you, if I put this into a coaxial line, I'm going to have losses. So the only option I have is to put the antennas on chip. But then how do I get the signal out of the chip? Because chips are made of semiconductor, higher refractive index than air. So waves like to stay on the semiconductor. They will tend to radiate in the opposite direction. Well, there are two things you can do. Okay, let's say we put the antennas on chip. Okay, and we go for this unguided interface, because I'm going to radiate. As soon as it's free on space, you are free of losses, as I showed you before. So our challenge is, how do we put the signal out there in space? Well, one way is, look, signal is going to go on the chip. So the only thing you can do is what engineers do, create a transition from the chip, which is going to be radiated, to air. And one of these transitions is silicon lens. And basically, we put a planar antenna on next to the photodiode. The signal, of course, is going to go into the indium phosphide, and then we put this lens. This lens collimates this radiation. Of course, this substrate has to be thinned down, sometimes to crazy numbers like 100 microns, even lower, very fragile. This is challenging. And then there is another challenge, is where the center of this lens is. Because there is a focal lens to that lens. It's a focal point to that lens. And you need to put this in the focal length. So you need to develop very accurate positioning of the chip on the lens. Okay, I'm going to have to take 5 more minutes myself as well. Okay, the other option is, okay, problem of the lens. Forget about steering, because you already have a lens that is going to direct the waves into a preferential direction. So, other problem, indium phosphide is not cheap. And as I told you before, we want to thin this down to micron level. It's fragile. If you have to put an antenna on top and increase the size, your yield is gonna kill your devices. You're not gonna be able to make money out of it, basically. So this is very challenging. The other option is, okay, let's go, there is another type of antennas in which on-chip antennas, in which I don't have to put a lens because I'm going to launch the radiation on the edge of the chip, end-fire antennas. I'm not going to need the lens, okay? And still, your radiation is going to see that this is a chip. You cannot launch it into the air, because then you will have the same hard interface that is the step change in the refractive index. So basically, people have devices, I'm going to launch it into a waveguide, and they are using, this is from a work in Osaka University and Adelaide, in which they use this effective index medium. And you create a waveguide, and then you put it into a waveguide. Okay? That's one way to go. The other way is, okay, let's see if I can put a guided interface, and I can put these different types of microwave lines in the chip. You're gonna have to launch it as soon as possible, because these are still lossy. Yeah, you have to decide between slot line, coplanar, and coplanar stripe. That will depend. Coplanar stripe, actually, that's the transition you are going to have to put if you want to even build this end-fire antenna. You are going to need a slot line in between. Coplanar waveguide usually is if I need to place a probe on it with GSG, I'm going to need this type of waveguide. And when we go to packaging, because these chips are going to need to be packaged, I'm not just going to sell you a chip on a lens or a chip. Basically, the interfaces that we have are either coaxial or rectangular wave. So I need to consider this, because these are the connectors that I'm going to have to put in my package. Problem is that if you look at these three types, I don't know which one I would name the good, which one is the bad, and which one is the other. Okay, just put it there so you can make your choice. But nobody's perfect. Okay. If we go to microstrip, this is what I have to put in my chip, because my chip is basically a substrate. So I have to lay out a microstrip line, and dispersion is low, bandwidth is high. That's good, but then loss is high. Okay, this is gonna kill me. And the other, well, photonics cannot give you much power, so we can live with this. And the rest is good. So my perspective would be, okay, this is the good. Rectangular waveguides basically is the connectors at high frequencies above 100 gigahertz basically use rectangular waveguide because of this. Again, loss is a key deciding factor, key figure of merit when you have to decide, because we don't have much energy. If you don't have much energy, you have basically no choice. We have to use rectangular waveguide, and the problem of rectangular waveguide is the dispersion of the signals, and bandwidth is limited. I will show you a picture immediately. And coax Well, coax is the most standard use, below 100. They are pushing it above. The problem is loss is medium, so still integration is hard. I need to make a transition from the plane to the coaxial. So, as I was saying, problem is loss. So what do we do? This is an example that we did some years ago. I always like to bring it because it was our first integrated microwave photonic chip fabricated within a project that I coordinated. And this chip was fabricated by 3-5 Labs. And actually, come to this. Basically, what you can see here is the photodiode. This is where we convert the RF into coplanar waveguides, these GSG bands. Problem that we had with, we are happy with dispersion and bandwidth. Losses, it's high ohmic as we increase. It's hundreds of dBs. In package level, we have, as I show you, coax. Coax is reaching up to 220. This is the maximum frequency you can actually find, and it's not commercial. And this is rectangular waveguide, which, as you can see, the problem is that is bandwidth limited. If you want to use a terahertz system for spectroscopy and you want to scan across different frequencies, you cannot use rectangular waveguide because it would be a pain to be changing. You will have to be changing. Actually, you would need different emitters because if you package in this, it will not go higher. We did this with this chip. We did this exercise to package it, and you can see here what we did. And as you can see, this is the photodiodes. And as soon as possible, we converted the GSG pads into a low-loss substrate. This is an RF Rogers low-loss substrate. And as soon as possible, we converted and launched it into a rectangular waveguide to avoid losing our signal. There wasn't enough power to accept losses in between your point of generation and where you want to deliver. And with respect to the access, basically it was the same thing. We are on high frequency substrates, which as we move above in frequency, increase the losses, and converted as soon as possible in the chip. We make it the contact as short as possible because of the losses of the RF there. More problems to high frequencies. So this is the size of the rectangular waveguide. This is the size of the rectangular waveguides as frequency increases into the terahertz. You see that the feature size is few microns. It's extremely hard, it's extremely expensive to build these low loss waveguides that we need. The other problem, yes, size becomes smaller. And then if you try to probe, if you try to test your circuit, you have to do it on smaller and smaller feature sizes, which is expensive, and your calibration degrades. And actually, what you can see here, this is a calibration substrate. You see the size of this calibration substrate is extremely small because at those frequencies you have so much losses that probably you will not have signal going through if you make this longer. So there is a huge problem as soon as we move out of the photonic domain into the RF at high frequencies. And this is where we took this leap. We thought we cannot push the technology that we have. We have to do something new. We have to jump out of the current technology. And with this, thanks to a European project that I'm coordinating, still alive, one year ahead of us, just actually finishing next November, is a future and emerging technologies project that the tribe is developing a new type of vector network analysis to reach into the terahertz range. to make a device that can test your circuit from DC to 3 terahertz. And okay, we had to deal with the problem that how do we generate energy over such a broad frequency range, and how do we connect those? Because there are no interconnects at those frequencies. So again, for the generation, we rely to photonics, because photonics, basically photonic frequencies is 193 terahertz. So generating a few terahertz is going to be easy. Basically, what you see here is the probe. And what we have is a photodiode. This photodiode is not a regular photodiode, because I show you that if you make a chip, basically it's a square die that has a problem. It's a resonator. And if you generate frequencies in that die, the frequency resonates. It's so high that the small size of the chip is already like a Fabry-Perot structure. So we have to develop a new type of structure that guides the generation, because we are dealing with waves. It's not an optical wave, it's an optical wave and an electrical wave. And our photodiode has the structure of our waveguide. That's first improvement that we did. And the other is that your signal, if it's generated on a photodiode waveguide, you need to launch it into a waveguide. And we developed these silicon structures to guide the signals into a connector that has the same bandwidth as the waveguide in which we put the radiation. So now we have the electric waveguides. We are using the electric waveguides which have no loss. Ideally, this is high resistive silicon, has 0. Is the fiber of the terahertz. Okay, and with this with which we generated 3 European patents. These have been submitted, and we are already asked for PCT extension for world patents. This was pushed by European Commission. If you generate new knowledge, you have to protect. We wanted to protect, and I'm going to show you a bit how this works. This is the electric waveguide that I show you. These are the substrates where we have the launchers, and we are launching the signals from this 100 gigahertz extension heads. This is a VNA with 100 gigahertz bandwidth. This is what the simulation gave us. By design, we selected this low frequency, starting at around 50 gigahertz, and from there up to 350, we don't see any issue. We don't see problems. And this already covers 4 rectangular waveguide standards. So we have a new type of waveguide that covers all these frequency ranges. But this is the theory, and this is the demonstration. And well, actually now you see here there is a roll-off, right? This roll-off is due to these connectors. We have to use coaxial connectors to launch a signal in our launchers. So this, what you see here, this roll-off is due to these coaxial connectors. But if you compare coaxial connectors to the same structure using a CPW with CPS, microstrip lines, if you compare the introduction of the waveguide with the structures with microstrip lines, there is no difference. We have a transparent media to now work with terahertz on chip, because this can be converted into a platform. And you can ask me, well, but you know, here you are injecting just one frequency. VNAs basically inject one frequency and measure the attenuation and the phase. So basically, this is for one frequency signal. Okay. We took note of that and did this demonstration. And we actually had to rely on photodiode and Schottky receiver. In between them, we actually put our waveguide. And this is the experiment that you are seeing here. We modulate light and create an RF signal. Basically, we don't generate one tone. We actually generate data modulated signals. And what you can see in this with a 16-bit quantum signal, complex signal, basically you see that there is no difference between back-to-back. That means connecting this photodiode to directly by rectangular waveguides to the Schottky receiver, as to the introduction of the electric waveguide. There is no difference. You can tell me, okay, I see the two traces, so I see a difference. Well, yeah, this was manually aligned, and that's why we blame this on the manual alignment. And with these patents in hand, we contacted Bullnet, and they were interested to launch our new adventure. And we have started a company that's called Microwave, about broadband interconnects. That is to put all the speed of photonics into your electronics using this new type of interfaces. I think I've already overrun too much, so no problem. This is not my last slide. Okay, this is not my last slide. I still have a few about addressing the power, because I've told you about overcoming the losses, but still is okay. But how can I put more power into the system? And I told you, the problem is about being in this in-between region. So there are a few schemes that you can do. Actually, in photonics, we still have 60 dBs to go to get to the limit. So we need component improvements, and we need to reduce the losses at the interfaces. I already told you about how to get to reduce this in the interfaces. There is another thing that we can do, that is to combine multiple emitters. And that's something that is really interesting. And it's something that can be enabled. People have tried different ways with end-fire antennas. This is 1D. So no, I don't want just 1D arrays. Then, okay, planar antennas. Here you have these resonant antennas, dipole antennas, and then I can distribute it. No, because this will not radiate upwards. I already told you this is a trick. It will radiate downwards into the chip. So have to do something else. We tried this. This is a complementary antenna with our colleagues. We are collaborating in Grema group at UC3M. Still, you need a lens. And what the Lionics did, going into microstrip lines, no, because then you still have the losses of the coaxial connectors. So what do? Again, we go to the dielectrics. And then what we're doing, and this is within another EU project that it's called TeraWay. What is the problem? That silicon lenses are too big. Then you can reduce it. Basically, the waveguide that I show you, the tapered end of our silicon structure, basically we cut it and you glue it to the element, and this acts as the interface element by element of the terahertz into space. And actually, you can see the radiation from two elements in phase. So you get all the radiation in the direction, in the transmission direction. But if you apply different time delays to the elements, you can achieve beam steering and you can actually switch. And if you can do this in 2D, actually if you can build a 2D array of photodiodes, which can be done, you can actually build 2D arrays. And this is the way we are going. Problem is that, of course, this is an assembly problem. And this is where we are. Microwave photonics is a problem of, at the end, it's a problem of assembly and packaging. And this is a key point that we are trying to make people sensible that it's a way to go in these funds that are being deployed in semiconductors. Because high frequency is going to be there and it's going to be a problem. And there are not too many people expert in this. While in Spain, we have a huge community that with expertise. Basically, to end, acknowledge the funding on the two active EU projects. Actually, this one will have a continuation in the 6G SNS, and we will continue developing these 2D arrays because they are too difficult for just one project. And then I would like to thank, this is the team that is working on these problems. Alejandro Rivera comes from the RF world, and Daniel comes from the photonics world, and Musin, it's in the in-between. It's the transition between the two. And this is the team developing this technology. There are more people in the company, out of 6 people in the company. And we will be looking to hire people somewhere soon. Thank you very much. And thank you for your patience.
Thank you very much, Guillermo. And now